Welcome back to the Home Lab, and I've got an interesting and counterintuitive bit of physics to look at today, and it's a question that's been doing the rounds. The question is, when you design an aqueduct, does it need to be strong enough to support itself, the water actually in it, and any number of boats that will also go across the aqueduct? So we're going to solve this problem with a little bit of field work and a practical demonstration. So just to reiterate the problem, you're a designer of aqueducts and you're thinking, how strong do I need to make this aqueduct? So you're thinking about the stone that you're building it with, you're thinking about the tubs that sit on top of the pillars, and also you need some estimation of the amount of water that's going to sit in the aqueduct. Now, you know that there are sort of weirs and spillways and things downstream and upstream, which keeps the canal at a fairly constant level. That's why canals don't typically flood like rivers do when there's been very heavy rainfall. So you've got some idea of how much water is going to sit in it. But the problem you've got is what happens, particularly with a very long aqueduct, when you get more and more heavy canal barges coming across the aqueduct. How much stronger do you need to make it? So the more you think about this, the more you think, well, you've got to add some strength. And then you think, well, maybe you haven't. And what happens if a boat comes on one end and goes off the other end? So give some thought to what you think the designers must have thought after they'd done their calculation without boats. How much did they need to add to their strength calculation to take into account the boats that were going to come across the aqueduct? Not far from where I live, there are some pretty impressive canal aqueducts designed by the master himself, Thomas Telford. I've driven boats over them, which is a great experience, but not one where you want to trip on the deck and take a tumble off the far edge because there aren't any railings. This is the impressive aqueduct at Chirk, built in 1798 and 22 metres high. It's pretty impressive. We're lucky that when we visited, family crossing the aqueduct invited Barry and Mum, whilst I was filming, to get on board their boat for a crossing. So that's really quite special. So with that in mind, did Mr. Telford have to take into account all of those years ago that this would happen? Well, let's do an experiment and find out.
.496 grams.
So after a bit of experimentation in the garden, the first thing to do is to take our aqueduct and to fill it with water. Just ignore the reading on the scales. What I've done is set the zero as far back as possible. So let's get this filled up. So with our aqueduct full, it's ready to start the experiment. But just before we begin, I'm just going to push down on the tank to show you that the scales are still reading. Okay, it needs quite a force, but they are still reading. So we'll get our pig boat and put it in and see if we get any change on the scales. So here goes with the boat. Watch the scales carefully. If you remember, I did zero them as far back as I could, so it can also take the weight of the water. But the boat, if you remember, was about half a kilogram, just under half a kilogram, and there's a big metal bolt on it there. So let's see what happens to the scales when we slowly add our half kilogram boat to the aqueduct. And Barry's better at this than I am. Let's put the passengers on board. There we go. And I hope you noticed, and maybe you guessed this, rather surprisingly, the scales don't move at all. So very quickly to explain this, you might have noticed that when I put the boat into the water, water spilt out from the sides. Now that's typical of a canal, because the canal has spillways, which means the canal keeps its level at all times. You don't see canals flooding. And if water can spill off those spillways, either at the far end of the canal or from either side of the aqueduct, then when we put the boat in, it will, because it's floating, displace its own weight of water. So if you think about it, we add the weight of the boat, but we displace that weight of water, so the aqueduct itself, with the water and the boat, doesn't get any heavier. Now, it's worth pointing out, of course, that that's fine for floating objects, but it doesn't apply to the horses that were towing the boats along the towpath that was actually on the aqueduct, nor people walking on it, but they're not particularly heavy. I mean, the horse might be as much as a ton, I suppose, and I think barges have a displacement of 20 or so tons. And there's one more demonstration we can do. What happens if a boat sinks on the aqueduct? So watch the scales now as I put our lead block in. And you'll notice there the scales do read, because the block actually has a greater weight than the water it displaces over the spillways. So the whole weight of the aqueduct with all its contents has actually gone up. So I guess you shouldn't sink too many boats on an aqueduct. So, did you get it right? That if normal conditions prevail, you do not need to take into account the weight of the boats on the aqueduct, because of course they displace their weight of water off the sides. Anyway, I do hope you enjoyed this video, and remember that at the end I often cut in some bits that I haven't put in to the main body of the video, so do please stay and have a look at those, and also right at the end I'll put in some links that may be of interest to you. So do please subscribe to the channel, but anyway, I'll be making another video soon, and I do look forward to seeing you then.